recording. All right, let's begin chapter 3. Chapter 3 is about probability, as I said. We are going to learn about basic concept of probability in 3.1. And we're gonna learn how to calculate probability, but I will not go deep into it because we are going to focus on 3.2 and 3.3. It's about discrete random variable and continuous random variable. Actually, we only have time to learn for discrete random variable. We will learn about binomial distribution. We might not have time in Poisson distribution. And for continuous random variable, we are going to go over normal distribution. Okay, this is really important for us. All right, let's start 3.1 really quick. It's basic concept of probability. Let's see how many people are there now. We have about 15 people. That's good. Okay. All right. Probability, it's everywhere around you. If you look around you, it's actually happen everywhere. Because there are many unpredictable events, right? And one way we need to if you have unpredictable event, and you need to make a decision. So one way to make a decision is using a tool like probability to help you making a decision to consider the chance or likelihood of the event happening. Okay, so probability will help you to make a decision, say whether I should do that, do this. For example, today, as you can see, if they say there is a 55% chance of rain today, what does it mean? Does it mean like there's a chance like 55% that it will rain today? Maybe not. If the weather forecast say 55% of chance of rain today, it means that based on the historical data, the rain has been observed on 55 out of 100 days with similar weather conditions. It means that 55% chance of rain, it means that out of 100 days with the same weather condition, there will be only 55 days that it will rain. Okay, this is 55% chance of rain when they said it in general. Okay, and the way to calculate this, they use probability to calculate it. Okay, to help find this value. Okay. And we can see many applications of probability in games. If you are in games company and you need a lot of probability in your games because you need to put on the probability like of the chance of winning or losing, going away one or another way with the probability, and then you will win in another the other chance, the other gate or the other way that you go with the game. Or weather forecast, this one it's obvious, right? Or Google Map, Google Map need a lot of probability, the calculating the chance, right? And arrival time, insurance, stock market, and data analysis. See, it's everywhere around you, probability. All right. In statistics, we actually assign the number to indicate the likelihood or the chance of an event occurring. okay? And that value, we call it probability, okay? Right here, it's the likelihood of an event occurring. Let me change the color of the pen. Sure if I can do it. Okay. And the chance ranges from 0 to 1, so cannot be more than 1, has to be less than or equal to 1, and cannot be negative, so it starts from 0 to 1. So probability value can never exceed 1. Okay. 0 means no chance of occurrence, that there's no chance of that event will occur. And 1 means a certain event that will occur for sure. Okay, if you look here, see 0 means impossible event. That means it never gonna happen. Okay, and 1 means certain. Okay, means it's gonna happen for sure. Okay, so we use this value to help you make a decision. Okay, and for this one, if you roll a die, a chance that number 1 or each number will happen on top, it's 1 out of 6, right? Because there are 6 spaces on a die. Even chance mean maybe toss a coin. Oops. Toss a coin with head or tail. Even chance means the chance is 0.5. Okay, even chance. So chance of showing head is the same as getting tail from a coin. Okay, like that. And let's start with the first topic, first section of this chapter. 3.1.1, it's the sample spaces and events. Let's see the terminology, these two terminologies. First thing you need to know is random experiment. Okay, what is random experiment? It is an experiment. It is a process that provides an outcome. Okay, it's just an experiment, and it will give you an outcome with the following property. Okay, the experimental process and provide an outcome. There's a property for random experiment. It's not just any experiment. It is an experiment with the first property. That is before the experiment happen, before you do this experiment, the exact outcome is unknown. You don't know the outcome, but you know that there like you toss a coin, you know that it's gonna be tail or it's gonna be head, but you don't know what it's gonna appear after you do the experiment. Okay, and the outcome cannot be predicted with certainty, right? You and random experiment, you before you do the experiment, you don't know the exact outcome, and you cannot predict with certainty. You cannot predict that, oh, the tail is going to appear or the head is going to appear, or when you roll a die, you don't know if 1 is going to appear or any if 5 is going to appear or not. You don't know. It's a random experiment. Okay, and this experiment, the process can be repeated. Okay, can be repeated many times. Okay, so the experiment with these 3 properties, we call it a random experiment, right? And we call the set of all possible outcomes, we call them we call this set sample space. For example, as I said, we toss a coin, you get head or you get tail, right? So the outcome would be just head or tail. Then we call the set that contain head and tail sample space, okay? If we put all the outcomes that will happen from the experiment together, and we call that set sample space. So when I ask for sample space, it means you have to list all the outcomes out and put as a set. Okay, a set means like a group of things. We will learn it after statistics. I think it's in chapter 7. And with the brackets, and then you list all the elements in here. Okay, list all the outcome in here. And the notation, we use symbol S, and we list all the outcomes like outcome 1, outcome 2, and so on. Okay. All right. And let's see example. Okay. For example, the first one, let's consider for, this experiment. We have a random experiment of observing the gender of newborn babies at Hospital A. So here we're looking at, we are observing the gender of the baby. So there are only two, right? Either boy or girl. This is biological gender. So we have only two, either boys or girls. So the sample space here, sample space would be, we use notation S equals the set of B, comma G. This is the way to write down a set. Don't forget the brackets, okay? The brackets here. And B is for boys and G is for girls. Or you can list like this, boys and girl. This is fine too for sample space, okay? Or let's see an experiment of tossing a coin one time. Okay, you toss a coin one time. Okay, suppose there's a coin, so either it turns head or it shows tail, right? There are two outcomes. So sample space is a set of all possible outcomes. So S would be the set of H and T. H is for head and T is for tail. So we try to list out the sample space here. Let me put highlighter so to make it clearly. So if I ask you to write down the sample space, you just need to write down a set and list all of the outcomes in there, okay? Or if you toss two coins at the same time, oops. Yeah, I'm using PowerPoint in my iPad, so there might be problem. Let's see. Okay. Tossing two coins at the same time. So you toss two coins here. Maybe this is coin, 1 baht coin. So two coins here. So the outcomes, so it might turn like head or both heads or both tails, or it could be head and tail and head, right? So if you toss two coins at the same time, then the outcomes will be head, right? Head, tail, head, and tail. So 4 outcomes. So we list all of these out. The sample space, when you have 2 coins, the two one outcomes contains like two things, then you use brackets here. Okay, brackets and then head, comma head like this. The first head is for the first point and the second head is for the second point. Like head, 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 tail, tail, head, and tail, tails. So 4 outcomes. All right. Or if you roll a single die and observe the number of dots on the top face. Here, you have single die. Yeah, this is a die. Okay. And you observe the top head. The top face of the die and see what number that it appears on top. Then since a die has 6 faces, so there are 6 possible outcomes, right? So either it turns 1, 2, 3 until 6. So sample space would be just 1, 2, 3, 4, 5, and 6 because we are interested in the number of dots on the top face. So sample space, you list all of the outcomes that we are interested in, outcome of our experiment, random experiment. And next, if your random experiment is tossing 3 coins at the same time, what would be the outcomes? See, you toss 3 coins at the same time. How many outcomes are there? 3 coins, right? So the first coin can appear with head or tail. Oops. Sorry. I hit. Okay. Do it again. Okay, 3 coins at the same time. So the first coin, the chance will be either you get a head or a tail, head or tail, right? Head or tail. Okay. So each coin has 2 outcomes, so a chance will be 2 times 2 times 2. Will be 8 outcomes total, right? This is the way to calculate it. So each coin can turn either head or tail, so 2 ways to do it. And you have 3 coins, so 2 times 2 times 2, there are 8 outcomes. You need to list them out. So it can be head, 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 tail, head, tail, head, and so on. And the last one is tail, 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 right? So if you list all the outcomes out, there should be 8 outcomes. So head, 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 tail, and so on until tail, 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 right? You toss 3 coins at the same time. So list everything out. We call this a sample space. Let's see the next example. If our random experiment is still tossing 3 coins at the same time, but we are interested in counting the number of coins showing tail. So the sample space will be different now. If I say we are interested in tossing 3 coins, our experiment is just tossing 3 coins at the same time. So the outcome would be just like the face that appear on the coins. But if you add on a more condition for your experiment, if your random experiment is tossing 3 coins, but you are interested in count the number of coins showing tail, that means you are looking for a tail on your coins here when you toss a coin. Like if the one tail appear, then we count the number, then the number will be 1, right? This number will be 1 coin, okay? Or if it shows like tail, tail, head, then the numbers that will appear on the sample space will be 2, right? We count the number of showing tails. So the possible outcomes in your sample space would start from showing nothing, like you get all head means no tail. This will be 0 coins. So sample space will start from 0. That means no tails, right? No tails appear. So 0 means 0 tails, or 1 tail, 2 tail, and 3. It's a maximum, right? 3 means all the 3 coins show all tails, right? So sample space would be 0, 1, 2, 3. This is 0 tail and 3 tails appears, right? When you toss 3 coins at the same time. So sample space will be different from the previous example. Previous example, just tossing 3 coins, that's it. So you list off the 8 outcomes out, but here we are looking for the number of coins showing tails. So you have to look at your experiment, random experiment, and think of the possible outcomes and put in the sample space, okay? They are not the same. So you need to look carefully at the experiment. All right. I think you guys get the big picture of sample space now. Now we move on to the next thing, a new word, which is sometimes we may not be interested in the entire outcome, but if we are interested to just a subset of the sample space, okay, then we call that an event, okay? If you are looking for a subset mean the things that contained in the sample space. So a smaller thing, a smaller set of the sample space, we call it subset. We will learn it later on. So if you're looking for just the subset of the sample space, then we call that the subset of outcome in the sample space. We call it events. Okay, now we have sample space, we have random experiment, and we have events. Okay, and we usually use the uppercase letter for event. See, or alphabet A, B, C, the capital letter. Okay. Again, event is just a subset of a sample space, subset of the outcomes in the sample space. Okay. For example, if we consider a sample space of we have experiments of rolling a die. Okay, we roll a die, just one die. Okay. We roll a die and observe the number on a die. Then let E be the event of even number right here. E is a subset of sample space, right? The event of rolling an even number. Then we can list the elements of E out like this. So sample space, rolling a die, sample space is just the number appear on the top face. So it could be from 1 to 6, right? And E, we are interested in experiment an event, okay? Event of getting an even number, okay? So it's gonna be 2, 4, 6, like that. So it's a subset of sample space. E will be 2, 4, 6. That's it. We are in event is just the thing in the sample space. It's a subset of sample space. Or if you toss 2 coins, okay, toss 2 coins at once, and let A be an event of getting at least 1 head. Okay. Then if we list all of the outcome in the event, Okay, you're tossing 2 coins. We did that before. The sample space would be head, 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 tail, tail, head, tail, tail, right? So getting at least 1 head would be head, 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 tail, tail, head, right? And this is sample space. We did that before when we're tossing 2 coins. So there are 4 outcomes. And an event here, if you list them out, at least 1 head, that will be head, head, see 2 heads, 1 head. And tail means no head. It's not gonna be in this event because we need at least 1 head. All right. If you have question, you can ask me or type in chat box. Okay. All right, let's see example 2. If we have an experiment of randomly choosing a number from 1 to 10, okay? An experiment, we need to choose number from 1 to 10. So what you will get for the outcomes, you will get either number 1, 2, 3, 4, 5, 6, up to 10, right? So you pick one number. So we list all the outcomes out and we call that sample space. Part A, we need to write down the sample space. Okay, S, you're looking for S. B, if E1 be an event of getting an odd number, write down E1. Okay, E is an event, is a subset of the sample space. So E2, event of getting number greater than 7. Okay, and write down E2. So here sample space is easy because you're choosing number from 1 to 10. So S would be just contains as a number from 1 to 10, right? The outcomes, all the outcomes. And E1 is just odd number. So 1, 3, 5, 7, 9. E2, number greater than 7. So 8, 9, 10, right? Have to be greater than 7. That's it. Not that bad, right? Or Ellie tosses a coin and roll a die. Okay. Toss a coin and then roll a die. You do two things. Okay. Toss coin and roll die. Part A, we are looking for what? Identify random experiment outcomes and sample space of this experiment. So random experiment, it's gonna be tossing a coin and roll a die, right? Outcomes, it's gonna be the head that appears and also mixed with the number appear on top, right? So outcomes, it's gonna be in the sample space. We will list them out. Part B, I will write down later. Part B, let A be an event of getting a head and number less than 4. And we need to list, write down A. B, be an event of getting tail and even number. Okay, so you roll a die and toss, you toss a coin, sorry, toss a coin and roll a die. So the outcome would be what? If you get head, right, and get 1 on a die, head 2, head 3, and head up to head 6, and then you change to tail, right? Tail 1, tail 2, tail 3, and keep going. So the sample space will contain 12 outcomes, right? So there are 12 outcomes on for this sample space, inside the sample space. So either hit 1, you get hit on the coin, and you get 1 on a die, and keep doing it until the last one you get tail from the coin, and you get 6 on the top face of a die. So there are 12 outcomes. Let's see A. A getting ahead and number less than 4. So it's gonna be what? Head 1, head 2, head 3. That's it, right? Okay, head 1, head 2, head 3. Because the number on the die has to be less than 4. Okay. B, getting a tail and even numbers. So tail 2, tail 4, and tail 6, right? Even number on a die, but fixed with a tail, right? Okay. Any question? These 3 examples just to introduce, okay, or help you to understand the sample space, event, and random experiments. So you should be able to write them down. What should be in the sample space? What should be in the event? Event is a subset of the sample space. Okay, let's find the probability. I will not go deep in this section. Actually, there are a lot to go in to find probability of different events. We just do just in general, just the concept. Okay, and to find the probability of an event, there are 3 ways to do it. And probability, again, probability of an event is just a number between 0 and 1. Cannot go more than 1, okay, and cannot be negative. And it indicates the chance of a trial, okay, that we are, or a chance of the things, an experiment or the thing that we are interested in. And there are 3 ways to find probabilities. The first way is use just your intuition. So it's intuitive approach, okay? You just use your opinion, use your guessing. Part 2, the method 2 is relative frequency approach. So you count the frequency and find the probability. And the third way is the classical or theoretical approach. There's a formula for it to calculate. Let's see number 1, intuitive or subjective approach. The probability with this way, the probability is estimated by using personal experience or use personal opinions. Okay, because it is really hard to gather the information or the data to calculate probability. For example, let's see. Find the probability that the next 1,000 baht bill you spent was previously spent by Lisa Blackpink. We want to know the chance, like if for the chance of the 1,000 baht bill that we spent in your hand, the 1,000 baht in your hand was previously spent by Lisa Blackpink. In this way, we don't know anything. We cannot collect data or anything. What we know, what we can do is just use our opinion, right? In this way to approximate probability. This is hard because we don't have enough information on the circulate to calculate exact probability is really hard because we don't know the information on circulation of 1,000 baht bills, and we need to know Lisa's spending habits as well in order to approximate or estimate the probability. So in this case, we just guess, okay? Let's say it would be 1 out of like 100,000 chance. So it's gonna be 0.00001. It depends on each person's opinion. With this method, it's not recommended for the probability, but in some case, it's not avoidable Okay, so if it's like this, then just use your opinion to find the probability. Okay, like that. The second method is relative frequency. That means we use frequency to calculate probability. Okay. In this case, we need to do experiments many times to get the data. So it based on the data from the table. Okay, so you need to go out and collect data, do experiments many times, and count the frequency of the number that event A occurs. Okay. Right now, we are looking for probability of an event. Okay, so we count the frequency and use the notation f of a for the frequency of event A. Then the probability of event A occurs is just, we use p as a probability. Okay, PA means the probability of event A. It's gonna be, you set the frequency on top and then divide it by the total number. Okay, this is the frequency and total number of experiment. Total. Okay, like that. For example, if you do a survey, okay, with 100 students regarding the courses that are currently studying, and the data is shown below, okay. There is a survey of you have 100 students, right, in the survey, and the subject, they are English, math, and computer, and split genders as male and female. Okay, let's see. For example, we have 16 males that study English. We have 20 males study math, and 32 study computer. And we have the total number down here. Okay, in the bottom row. Okay, we need to find what? Find the probability of the following event. A, find the probability that student enrolled in math course. Okay, let's see the next page. Okay, and B, find the probability that male student enroll in computer science course. The first is just any student, both gender, male or female, study math, right? So I'm gonna do it here, the table, and we're looking for the first thing, student enroll in math course. So math course, student enroll, we are looking for a math course. So both male and female, we have 29 students that enrolled in math course, right? Out of 100. So from here, let A, okay, we need to let alphabet A be an event of student enrolled in the math course. Then PA would be frequency over the total number. So we have 29 people study math, right? Both male and female. So it's gonna be, you set frequency 29 out of 100. So the chance that a student would enroll in math course is 0.29. So probability cannot go more than 1. Keep that in your mind, and cannot be negative. Okay, so this is set the frequency over the total number. And B, so we let B be the event of males student enroll in computer science course. So male study computer, it's right here. There are 32, right? 32 students, male students studying computer. So PB, probability of an event B, is gonna be 32 out of the total number is 100. So 32 over 100 is 0.32. That's it. And another example, let's see. Jerry rolls a die 50 times and observe the number on the die. And we have the result out here. So there are 50 data in here. Okay, 50 number of data with result here. So for this case, if the data comes in table or just like, like a list, comes like list them out like this, of the outcomes, then to find the probability is really easy. You just count the number of outcomes in the event and then divided by the total number. All right, so we are looking for the probability of getting number 6 on the die. Okay, getting number 6, so you just count number 6, like 1, 2, 3, 4, 5, 6, 7. There are 7 of number 6, right? So getting number 6, let A be the event, okay, of getting number 6 on the die. Then probability of getting A, just what, 7 over 50. That's it. So it's gonna be 0.14. Now part B, you're getting number less than 3 on the die. Number less than 3 means you don't count 3, right? So it's gonna be just 1 and 2. So you count 1 and 2 here. 2. See, you count them all. I have already counted. So there are 15 of them. Okay. Number less than 3, 15 numbers. There are 15 numbers. Okay. So it's gonna be 15 over 50, right? See, the probability is we calculate that, use calculator, we get 0.3. Okay, so we have a chance of getting number less than 3 is 0.3, and a chance of getting number 6 it's 0.14. So that means getting number 6 is really like half chance of getting number less than 3 for this experiment. So you can estimate roughly, oh, it's like less likely to happen like that. All right, just count the frequency. If the data comes like this, it's not bad. Now move on to the third one, the classical or theoretical approach. Okay, here you need a formula. The third method is really classical and people use it a lot to calculate the probability. Okay, and the probability that we calculate is just, well, we use the number. Okay, the number of finding the probability here of an event. Suppose E is the event, okay, that we are interested in. Okay, so to find the probability using this way, you need to count, okay, the number of outcome, okay, and E, number of outcomes, okay, in the event over the total number in the sample space. Of course, with this method, you need to list out the sample space and you need to list out the element in the event, okay? Number of all outcomes, okay, in sample space. All right, so just number of outcomes in the event and over the number of outcomes in the sample space. This will give you the probability of the event E. All right, let's see example. Consider experiment of rolling a die again. Simple example. Find the probability of getting number 5 on the die. Okay, getting number 5, and B, getting even number. We did this many times. So the first step that we should do is just give alphabet to represent the event. Maybe E1 be the event of getting number 5 on the die, and E2 be the event of getting even number on the die. So in this case, we need to list out is sample space. Okay, we need to find sample space. Okay, rolling a die. So there are 6 possible outcomes, right? Either you get 1, 2, and up to 6. So sample space would be set of 1, 2, 3, 4, 5, 6. Now, next, you need to list the event, okay, out. So list E1 out and list E2 out. Part A, so E1, getting number 5, so it's just a set of 5, right? Get just 5, just one number appear on the die. And B, E2 is the event of getting even number on the die, so it's gonna be 2, 4, 6. So with this method, we need to count the number. Remember the formula? Count the number, NE is the number. We need to count a number of elements in E over the number of elements in S, and we divide the two numbers. So counting the numbers here, NE would be just one element. And in E2, there are 3 elements, and number of elements in sample space, we have 6, right? So that's it. And to find the probability, we just divide the two numbers. So NE1, the number of elements in the event, so it's 1 out of 6. That's it. Number of elements in E2, there are 3 elements, so 3 out of 6 will be 1/2. Okay, so probability of E1 is 1/6 and probability of E2 is 1/2. Next, assuming, let's see example 7, assuming boys and girls are equal likely to happen, okay, and find the probability of getting, now we're getting 3 children all at the same gender. This is the event, okay. We are interested in getting 3 children all of the same gender when 3 children are born. So you need to figure out what would be in the sample space, what would be in the event. Now we are interested in the newborn, 3 children, right? 3 newborns at the hospital. I don't know where. We are looking for 3 newborns, right? And we're looking for the gender. So let E, okay, finding probability of what? That thing would be event, okay? So E will be the thing that I underline, be the event of getting 3 children of the same gender. Now the sample space is something bigger. We are looking for 3 children, right? The gender of 3 children that are born. So sample space would be just either, okay, B, boy, boy, boy. And G stand for girl. Either B, boy, 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 girl, BGB until we get all girls. So there are 8 outcomes. for the sample space, right? Same as tossing the coins. And E, getting 3 children, all of the same gender, mean you get all the boys and all girls, okay, like that. So we count the number of elements in the sample space, which is 8, and count the number of elements in E, which is 2 elements. We count number of elements, and so that the probability of an event E is just NE over NS. Oops, which is 2 over 8. So 1/4, or if you want decimal number, it's gonna be 0.25. So 1/4. Okay, the chance of getting the same gender is just 1/4. That's it. This is the way to find probability. Not bad, right? Or let's see example 8. In a study of the US high school drivers, okay, what we have, it was found that 3,785 text while driving. Hope you don't do this during the previous 30 days. And there's a data here, another data. 4,720 did not text while driving. Okay, during the same period means in the previous 30 days. If a high school driver is randomly selected, we are looking for find the probability that that person, if one person is selected, find the probability or the chance that that person texts while driving. Okay. So we're looking for probability. So we're gonna set this comes in frequency, right? It's gonna be the second method, but we need to know the total number, right? In this case, we need to know the total number so that we can divide by that number. So we're looking for let A be the event. We are looking for an event that high school driver takes while driving. I mean, you are looking for a chance that if you pick one person, that person would take while driving. Let's see the chance of that person would take. So we let A be the event that we are interested in. Okay, a high school driver takes while driving. Then we need to find the total number of drivers. So there are 3,000. Oops. I hit the wrong button again. Okay. 3,000. Hold on. 3,785 takes while driving, and 4,720 did not take. So we add these two numbers together to get the total number of people in the surveys, right? High school drivers that they took a survey. So you add these two, you get 5,820. Add 1, 14, 15, add 1, what is it? 8,505 people, total number of drivers, right? So from here, you can find the probability. So you set the total number of outcomes in the event or the frequency in this way. So event of high school driver takes. So takes, there are 3,785 people over 8,505. So I need calculator to calculate this. It's gonna be 0.445. Okay, this is a chance. Okay. of if you pick a high school driver and the chance that that person would text while driving, wow, it's about 0.5. That's a lot, right? 0.4, 0.445. Mean high chance, half chance, right? Even chance. That is not good. All right. And I think this is enough example. So for probability, I will go just only this much. Okay, I will not go deeper than this because we have a lot of things to do, which is more important than finding the probability in other ways. So next, you can skip this and you can go practice on this problem. We have answer and we have probability and rules. Keep in your mind that probability cannot go more than 1 and cannot go less than 0. Okay, and probability of the sample space is 1 because the chance that all the outcomes, chance of sample space contains everything. So the probability of the sample space is 1 and probability of empty set is 0. That's it. That thing you need to know. And the rest of this will not, not on the exam. I would stop with the probability here and I will move on to the second section. Okay. For the set operation and all things after this will not be on the exam. Okay. If you are interested in this topic, you can study on your own. Okay. And if you are interested, you can come see me. So for probability, would stop here and I will move on to 3.2. All right. Okay, let's move on to 3.2. And how do I stop sharing this? Okay, keep ink. So does it keep everything that we write down? Yes. All right, let's move on to 3.2 really quick. I'm gonna move on to part 2, 3.2, which is more important with binomial distribution and discrete random variable. Okay, so in 3.2, for discrete random variables, right here, the first thing that we need to know is random variables. We have random experiment in 3.1, we have sample space, and we have event, right? Different terminology. And in 3.2, we need to know about random variables, okay? Now, in the random experiment, there will be a number, okay, which is related to the outcomes, okay? And for example, if we are looking for the number of defective light bulbs, okay, the light bulb is broken light bulbs in a batch. That would be a number that we are interested in the random experiment, or the number of people entering a restaurant, or waiting time at the cash register when you're waiting to pay. Okay, and such a number is called random variable. Okay, it's just a number, random variable. It's just a number which is related to random experiment. Different from event. Event is a subset of sample space. So it just event is like a big set. And random variable is just a number, okay? Number which is related to experiment. There are two different things. So random variable is a numerical quantity or number which is generated by random experiment, which is different from event too. And this number might It varies from trial to trial, depending on the experiment, and cannot be predicted with certainty. We cannot predict, like pinpoint that, oh, it's gonna be this number. We don't know. And again, we use the same as event. We use the capital letter to represent random variable. And also we use the lowercase alphabet for little x, little y, little z, or little a, little b, you see, for the value of the random variables. Okay. There are two types of random variables. Okay. The first type is discrete random variables. So when the discrete means you can count. Okay. The values are finite or countable. Okay. You can count. Okay. For example, if you are interested in number of heads appear when two coins are tossed. So the number of heads appears, two coins are tossed. Number of head would be, there is no head appear, which means it appears like with two tails. So it's gonna be 0, 1, and 2, like that. This is not the event. We call it random variable, so no set. It's not a set. So we list out what we need to list out like this for random variable. So we list x and equals, and the number on the right side. And we use the smaller case to represent these numbers. And for the continuous random variables, means you cannot count. It's infinitely many values. For example, the waiting time at the cashier register. If T is the waiting time that you wait to pay, okay, at the cashier, it could be 0 means you don't have to wait at all. You go there and then you get to pay right away. And maybe less than 10 minutes. 10 minutes is really long. So it could be like from 0 to 10, like that. So it's a time waiting. You cannot count. In this case, it is continuous, right? It's just run infinitely, like continuously, not infinitely, continuously, because it's the time. So there are two types of random variables. Again, random variables are just number, okay? It is just number, which is related to the random experiment. For example, let's see more. If you roll 2 fair dice, okay, 2 fair dice, 2 fair dice, like that. And random variable, maybe you're interested in the sum. Okay, x would be the sum of the number of dots on the top face. Okay, x here. Then x would be the sum of the number on top face. For in this case, if you roll 2 fair dice, the outcome would be 1, 1, 1, 2, right? The number on top until 6, 6, 36 outcomes, right? There are 36 outcomes. Oops, I cannot write down here. So there are 36 outcomes, right? If you roll 2 dice, because each die has 6 faces, so 6 times 6 is 36. And you are looking for the sum of the number of dots. So 1, 1, the sum of number would be 2. 1, 2 will be 3. So start from 2, 3, and the last one, 6 and 6, give you 12, because it's the sum of number of dots. And in this case, the result is discrete, right? Discrete random variable. And the next one, if you flip fair coin repeatedly. Flip the coin repeatedly, many times, keep flipping. Okay, flip the coins and let X be the number of tosses until the coin lands head. You flip the coin until you see head on that show up on the top face. Okay, and the possible value of X would be start from 1. 1 means you flip, you toss just the first time and head will appear, or you toss it twice and the head appear, or you can keep tossing and the head never appear, right? So in this case, X would be starting from 1, 2, 3, 4 until forever. What if you would keep tossing and the head never appear, right? It's gonna be running forever, but the value is still discrete in this case, right? Because you can count. It's finite. You can count 1, 2, 3. You toss 2 times. You toss 3 times until head appears. Okay. And the third example, you measure the voltage of an electrical outlet. Okay. If you go to the outlet and measure the voltage, you of course you have a tool to do it. You don't put your finger in the outlet, right? Okay, let X be the voltage measure. So I think this one is American. In Asia, it's the voltage is until 220 or 240. So the value, okay, anyways, the value of X would be maybe range from 118 to 122. This is in America, maybe. And the value is not countable, right? You cannot count, it's the voltage. So in this case, it's gonna be a continuous. Oh. Oops, everything disappear. Oh. Discrete, this one is continuous. Okay. And next, operate a light bulb until it burns out. So let X, you are looking for the time until the bulb burns out. So it's the time you cannot count, right? It's gonna be continuous. And the time until it burns out, it could be like you buy it and it's defective. So 0 means it burns out right away. You use it and it's like, boom, it's broken. So X would start from 0 until forever. Your light bulb is really good. It never burn out. It could be, right? So X can be from 0 until, forever, infinity. This is infinity. So in this case, the type would be continuous, random variable. And for random variable, things that we are interested in is actually probability distribution. What is it? We're looking for, I think I mentioned the distribution before, but actually the full name is like probability distribution in this chapter. So we are looking, it is a function, okay? It's actually a function that gives the probability for each value of random variable. You can look at it as a function, and the input is just the value of random variable. The output is a probability. So usually we express in terms of graph or table like that. When you plot it like this, so value will be on the x-axis and probability, its probability will be on the y-axis. Value means value of x. So like for example, the first example, x range from 2, 3, 4, 5 until 12, right? The first example up top. And you're looking for the probability. You put 2, the chance of getting 2 with some probability, probability cannot exist 1. The chance of getting 3 with some probability, and then you plot it, and then you draw a distribution like that. For discrete, you draw like a bar. Okay. We have 2 types. For discrete random variable, it will comes out as a bar because the value of x is just like number. Okay. And for continuous, it runs forever. It's gonna be like smooth graph. Okay. So there are 2 types of distribution. We're plotting probability against the value of the random variable. And the value down here of random variable. Okay. All right. And the common probability distribution that we have here for the discrete random variable, there are so many distributions: Bernoulli, binomial, Poisson, uniform, multinomial, but we're not gonna study all of them. For binomial, for discrete, what we are going to learn is just binomial distribution. The rest you can, if you're interested, you can go and study on your own. And for continuous random variable, I'm gonna go over normal distribution and t-distribution. That's it. So 3 things that we need to learn. And they are the most important distribution, especially the normal distribution. This is really important. Okay. You need to understand what it is. All right, let's go move on to discrete probability distribution. Okay. All right, for the discrete distribution, it must satisfy the following requirements. The first thing, the random variable x, there is a random variable x and the number value, see there is a random variable x and its number value, of course. And each probability value must be between 0 and 1. Inclusive means it can be 0 and it can be 1. And the last thing, which is important, if you sum of the probability of random variable, you sum them all, you should get 1. Okay, this is the way to check the probability that you calculate for the discrete distribution. And the probability of discrete random variable, usually we write down like this as P of X. Big X stand for random variable. A small x is for its value. Oops, disappear again. Random var. Okay. And for short, we just write down P of little x. Okay, we call this probability mass function. If I use PMF, it's for discrete random variable. For the continuous case, we use something else. We have PMF and PDF. PMF is probability mass function. It is a probability of each random variable with value x, little x. Okay. Here we need to find this, the probability of each random variable. For example, let's see example, a lot of examples so you understand more better. And Consider an experiment again of tossing two coins, two fair coins. Okay, means it's not biased. Two fair coins mean the chance of getting head and tail are the same, are even, like 0.5 are equal. Okay, two fair coins. Tossing these two coins at once. And of course, there are different things to study. We have sample space, remember, tossing two coins. Sample space contains all of the outcomes. That means there are head, tail, tail, head, and tail, tail, right? Here, sample space. And if we are interested in this, let X be the number of heads that are observed, not an event, okay? If I talk about an event, then it will be a set. Remember, if A is the event of getting a number of heads, then A would be a set and list of the outcome that is a subset of S, something else. Now, for the random variable, it is just a number, okay? So we're looking for the number of heads that are observed. If X is a number of heads, so X would be number of heads, then there is no head, so both tail in this case, or one head and two heads. Okay, one. So X would be 0, 1, 2. That means the little x, the value for little x would be 0, little x would be 1, or little x would be 2. The little x is just the value of the big X. Big X is just, we call the name of the random variable, stand for random variable. Like that. So in this case, we are looking for what? We need to construct a probability distribution of X. Okay. Again, probability distribution, we need to do like either in table format or graph format that lists out of the probability, which is related to the value of X. And also we need to find the probability that at least one head is observed. That means we need to find probability of X, at least one head mean X greater than 1, right? Greater than or equals to 1, like that. So at least one head, so X being 1 or 2, right? In this case, because the value, there are 3 values here. Now, to construct the probability distribution, what we need to find is, we need to find P. You need to find P of X being 0, P of X being 1, P of, this is the way to write down, P of X being 2, like that. Find the probability of this. And we need, this is, might be challenging. You need to look back. To get 0 for a random variable X means there's no number of heads appear. So you go back and look in the sample space. Okay, no heads appear means this case, right? This is little when little x is 0 here. So this is P of 0. That means no heads appear. So the chance of getting no head, you go back and think. This is the case of tail and tail. So the chance would be the number, we count the number, right? 1 out of 4, right? So the chance of getting no head means one, you get both tails. So 1 out of 4, something like that. And for the second case, X equals 1 means one head appears. So you go back and look in the sample space. So the outcomes, number of outcomes at one head, exactly one head appears. There are 2 of them, either head tail or tail head. So it would be, this is P of 1, so 2 out of 4, right? 2 cases out of 4, and of course, the last one, 2 heads appear. There will be only 1 case here, okay? 2 heads. So only 1 outcome here, then will be 1/4 again. So you list off the probability out and you need to think a little bit. Okay, this case is from where and how many outcomes are there and how to find probability, all right? So list all the outcomes on the left of the column here. X is 0, 1, 2, and list of the corresponding probability. So P of X equal to 0 in this case, it's tail and tail, right? Head, tail, tail, head. So 2 out of 4, so we 2/4. In this case, 2/4, it's 1/2. And X equals 2, mean 2 heads, you get 2 heads, so it's just 1 outcome out of 4, okay, 1/4. Now check the property here. If you sum of the probability, you should get 1. So sum Px, check your work. Sum Px, you add 0.25, 0.5, and 0.25. You should get 1. Yes, we get 1. And we represent, this is probability. We call probability distribution. Okay, probability distribution means you list of a value and its probability out. If you plot the graph, this is a discrete case. Discrete means x comes as in value, like the number. You can count, okay? So you plot 0 and 0.25, you plot 1 here, and 0.5, and you plot 2 and 0.25. That, you can plot them, you can see it's really nice here. All right. And what are we looking for next? We find probability. Next, we need to look for part B, right? Find the probability that at least 1 head is observed. So we need at least 1 head, means we are looking for probability of X greater than or equal to 1. We need probability of X greater than or equals to 1. So for greater than or equals to 1 means you get 1 head or you get 2 heads, right? In this case, you need to add these 2 probability together. This is 1 head. This is the case for 2 heads, right? So what you need, because it say at least, mean you need to add all of the possible cases. So you need to add probability of getting 1 head, which is P of 1. So from the table, it's 0.5, right? And P of X equals 2 is 0.25. So you add them all together, you get 0.75 as a probability of X greater than or equal to 1. So at least 1 head. So the chance of getting at least 1 head is 0.75. It's really high. Okay. Any questions so far? All right, next example. A pair of fair dice is rolled. So you're rolling two dice, okay, together. 2 dice. Okay, and let X be the sum of the number of dots on the top face. So we sum the result, sum the number on the top face. So if it shows like 1 and 2, so the sum of the number would be 3. Now, what do we need to find? We need to construct probability distribution. This is a hard job because if they ask you to find probability distribution, means you need to find probability of each value of X and put in the table. Okay. And part B, we need to find the probability of getting the sum at most 5. Okay. At most 5 means no more than 5. Maximum is 5. And C, find the probability that the sum is an odd value. Means the sum would start from 2, right? Remember the sum of the dots. If you get 1, 1, then it's 2. 2 until 12. So odd values mean you get a sum of 3, 5, 7, 9, so on. So to start this problem, I suggest you to write down the sample space so that we can find the probability. Okay. Let X first. Okay. Sample space for this one, it's gonna be, because we roll two dice, right? So the number that show up on the top face would be 1, 1, 1, 2, 1, 3, until 6, 6. So there are 36 outcomes total. So the total numbers of outcome in sample space would be 36, right? And X, a copy from the top, X be the sum of the number of dots on the top face. Then what we need to find is to find part A, the probability distribution. So the sum of the number of dots. So you start from here, the sum of the number of dots. 1, 1, the sum would be 2, right? 2, 1, 2 would be 3. And keep going till the last one, 6, 6 would be 12. So actually the sum, the value for X would be 2, 3, 4, 5, and keep going until the last one is 12, because that's the maximum number that you could go. So X start from 2, 3, 4, and 12. Here we need to construct probability distribution. That means you need to construct this table. X and P of X equals little x. So list out of the value 2, 3, 4, and keep going until the last one is 12. You just keep going. Okay, there's a lot of work. And we need to think, okay? For X being 2, it comes from what outcomes? How many outcomes are there that give you the sum of 2, right? So in this case, to get 2, the outcome would be just from 1, 1, right? 1, 1. So 1, 1 means there is only one case, right? One outcome out of 36. So in this case, it's gonna be 1 out of 36 because there is only one outcome that have the sum of 2. What about 3? What outcome that give the sum of 3? It would be 1, 2, right? And also 2, 1. So there are only 2 outcomes that give the sum of 3. So 2 outcomes out of 36. I cannot write down 36. So it's gonna be 1 over 18. Like that. So 2 out of 36. Now what about 4? The sum of 4, that would be what? 1, 3, right? 2, 2, and 3, 1. So 3 cases, 3 outcomes for this one. So 3/36, like that. And keep doing this until the last one. The last one, 12. So the outcome for this case would be 6/6. So you need to think a little bit to get the probability out. So 1/36, right? It's only one outcome. List all the outcomes and its probability out. Then you get probability distribution here as a table form. Okay. So you keep doing this. You see a lot of work. When we talk about random variable, then we need to think back of the sample space and looking for the number of outcomes. Okay. All right. Here I give a summary sample space. So probability distribution, if you list them out, it looks like this. Okay. High chance would be 7, right? There are many outcomes that give the sum of 7. And if you plot the histogram, means you put the bar next to each other, remember? And you can plot like, okay, sum of 2 here, the value down here, and its probability as the y-axis. Okay, so 2 plot with 1/36, 3 plot with 2/36, and keep going. It looks like a bell shape. So x on the value of x will be on the horizontal axis like that. Okay, looks like a bell shape. All right, with experiment. Okay, finish part A. Part B, what are we looking for? In part B, we're looking for, go back a little bit. Part B, find the probability of getting the sum at most 5. So at most 5 means x has to be less than or equal to 5. And part C, getting x as an odd value. You can write like this, P of x is odd. Then we will look closely what to put for each case. When x less than or equals to 5, that means x can be what? X start from 2, right? Value of x could be 2, 3, 4, up to 12. So in this case, x less than or equals to 5 means x can be 2, 3, and 4, right? So you, 5 too, because equals to 5. So you add, oops, sorry. So P of x equals 2 plus 3 plus P of x equals 3 plus P of x equals 4 plus P of x equals 5. So look for the value from the table. When x equals 2, the probability is 1/36, and this is 2/36 plus 3/36, 5, 4/36, right? This is from the table 1, 2, 2, 3, 4, 5. Okay, so you add them all, you get 5 plus 5, you get 10/36, or 5/18 as a chance for x less than or equal to 5. Okay, part C, when x is odd. So when x is odd means x could be what? 3, right? 5, x equals to 7, and 9, and big X equals to 11. So add 5 probabilities. See, if you get probability distribution table, it's easy to work on other things like this. But if you don't have that table, then you need to think of each probability and then you add them all. 2 over 36, 5, so 4 over 36. I get it from the table. When X is 7, the probability is 6 over 36. When X is 9, it's 4 over 36. When X is 11, it's 2 over 36. So you add them all. 10, 8, so 18 over 36. Of course, it's just half of it, right? Odd and even. So the chance is just a half, right? So the chance of getting the sum of the number appears on top face is odd. The chance will be just a half, 50%, 0.5. All right. So this is a probability distribution and 5 probability of the certain situation for the random variable. If you have question, you can type in the chat box. Okay. Now, the next thing that we need to find with the random variable is the expectation or expected value and the variance for the random variable. And the variance and expected value are also called mean. These two values can be found a different way from what we did in chapter 2 because that one is just from the data, right from the data. But here it's for random variable. Okay, the expected value, what is it? It is just, okay, when we talk about expected value, it's the average outcome. Sometimes we call it mean, okay, or the average of the outcome that would occur if the event were repeated many times. So if you do keep repeated the experiment, okay, and keep doing that, and the expected value is the value that tell you like the average outcome that would occur, okay? Or if you toss if you look at the sum and the previous example, if you keep tossing the coin and do experiments many times, and if expected value is just 7, for example, if you calculate and expected value is 7, it means more likely that the sum that will show on top face would be 7, something like that, okay? But if you keep repeat experiment many times and expected value will tell you the average outcome that will occur. And it is also the mean. Expected value is also the mean of a large number of the selected outcome of the random variable. It's actually the mean. Expected value is actually the mean. It is also called expectation, mean, or the average. Okay. Actually, expected value is just the mean or the average in terms of in the topic of random variable. Okay. How to find it? There's a formula for it. To compute the expected value, expectation of random variable, the notation we use it as E. E stands for expected value, okay? E of random variable X. And we use mu for expected value, which is the mu that we use it for mean. So expected value is actually the mean or the average. How to find it? We sum the expected, we sum of the random experiment, the value times its probability, and then we sum them all. Okay, so you multiply probability by the x value here. You multiply them together, these two values, and then you sum them all. If you have 10 variables, then 10 values, then you sum them all. Okay, and you get expectation or expected value. For the variance, it's something different. The variance of random variable, there's a formula for it. It's the expected value of here, x minus ex squared. Complicated, huh? We actually calculate with this formula. So we do ex squared minus mu square, which means you need to sum xi squared times p of x equals to xi, and minus mu square. Mu means you need to find expected value up top. Then you get the variance. Okay. I will show you how to calculate this. It's not that bad. Or you can calculate from this formula. It depends on you. It's not fixed, but usually we use the formula, the first formula. Okay, this is the formula for the variance, and there's a formula for expectation. For example, of course, to calculate all of this value, we need the probability distribution table because we need all the probability out. For example, find the mean or expected value by ex and find the variance of, again, it's not with the data in chapter 2. We don't have the data like that. If you have the data listed out like that, we're looking for a descriptive statistic in chapter 2. There's another formula to calculate, but here we're working with discrete random variable x. So different formula. And in this example, it's good. They give you probability distribution table already. So we already have x and p of x equals x. For example, right here, the big X, the value is 1, 2, 3, 4, right? And they give you its probability already. For example, p of x equals 1 would be 0.1 like that. Okay, so to find the expected value, we use the formula from the previous page. So e of x is going to be sum of x times its probability. Expected value or mean. So e of x, okay, we do it one by one. We need to sum x. So the first x is 1, right? The little x here, 1, and times with its probability, 0.1. And then the next one, x is 2 times 0.4. X is 3 times its probability, 0.1, plus 4 times 0.4, like that. See, not bad. This is the way we calculate it. So x times its probability, that's it. So 0.1 times 0.8, 0.1 plus 0.8 plus 3 times 0.1 is 0.3. 4 times 0.4 is 1.6, right? You add them all, 0.9, 11, so 2.8, right? This is expected value, which is the same as mu. So on the average, if you keep doing this experiment many times, chance that you will get the result that you will get is about 2.8. Okay, averagely 2.8 will appear like that. So this is expected value. And for the variance, the way to calculate the variance, it's a little bit complicated, but not too hard, okay? The way to find the variance, the formula is expectation of x squared. So x squared means you need to do summation. Instead of x, you square little x first and then times with its probability like that. And minus mu or expectation squared. All right, so that's why we need to calculate this one first, e of x squared. So we need to sum x squared of p, big X equal little x, and we need to multiply this, your little x from the previous page. We have little x 1, 2, 3, 4, and the probability 0.1, 0.4, 0.1, 0.4. Okay, so 1 squared times probability is 0.1 plus x is 2, right? 2 squared times 0.4 plus 3 squared times 0.1 plus 4 squared times 0.4. All right. So 1 squared is 1 times 0.1 is 0.1. 2 squared is 4. 4 times 0.4 is 1.6. 3 squared is 9 times 0.1 is 0.9 plus 4 squared is 16 times 0.4 is 6.4. So you add this number together, 7, 8, 9, you get 9. Okay, so this is e of x squared. Then we need to find the variance. So variance is gonna be e of x squared minus mu squared. E of x squared is 9. Mu, we get it from previously, which is 2.8. And we square this. So you need calculator to help out. We get 1.16. And the notation for this is sigma squared. So this is the variance. This is the variance. And if you want to find the standard deviation, you can find it, remember? Standard deviation is just sigma, so square root of variance, which is square root of 1.16. This is extra. And you get 1.77. So you get variance, you get standard deviation. SD is a standard deviation. Okay, I think this is the last example that we can do today. I thought we're gonna finish binomial, but it will be too much for you guys. Okay, example 4. Suppose in a certain game, there is a 5% chance of winning 100. And, okay, let's see. In a certain game, there is a 5% of winning 100. Yeah, maybe in a casino. 5%, they said, okay, if you go walk into the casino, they already set a chance of winning, chance of losing in the machine, slot machine or whatever machine in there. For example, here, they said 5% of winning 100 and 50% chance of winning 0. Okay, see, that means you get nothing. And wow, a lot. 45% chance of losing $20, more likely to happen in the casino. All right. From this data or information, we can work out here. Find the expected value and the variance of winning, and then we will interpret what it is. And part B, what should the player expect from this game? Here is the good use of expectation or expected value. Okay, this is in some application. From the data, we should write in the table form, put the data in the table form. So right now we have the information about the percentage or the chance. We talk about the chance, so that thing means the probability, right? Chance means probability. And we also have the amount of winning, amount of losing, right? So from this data, I put the table for two things. So the amount, which is gonna be our random variable, x here. Okay, actually, let's see. Okay, let x be the amount, okay, of winning. All right, so that means your x, the amount of winning would be 100, right? Right here with a chance of 5% mean 0.05, and amount of winning 0, a chance is 0.5, 50% mean 0.5. A chance of winning, well, losing means gonna be winning negative value like that, minus 20 with a chance of 0.45. Okay, so from here, part A, find the expected value and the variance of winning. So EX, it's gonna be sum of X PX. Okay, so we multiply, okay, 100 times the chance 0.05 plus 0 times 0.5 plus minus 20 times 0.45 like that. So calculate this value out. 100 times 0.05, you get 5 plus 0 minus, right, minus plus minus 920 times 0.45 is 9. So minus 9, you get minus 4. Wow, you actually, this is the dollars, the amount. So you actually losing money. This is the expectation or expected value. Okay. So from here, I will calculate the variance on the next page. So from here, we need to find the variance as well. But let me put a conclusion first. What should we expect from this game? Remember the expectation, it means the average outcome when you repeat it, the experiment many times. That means when you keep playing, right? In this case, when you keep playing many times, chance that you will lose $4 will happen. That, right? We expect to lose $4 in the casino. Okay, from here, you can tell, you can calculate it yourself. So it means, conclusion here, if we play the game many times, we would expect to lose $4. Okay, each time we play like that. All right, let's calculate the variance. I need to add a page. How do I add a page in here? I need to go to the main page. Insert. Oh, here. All right, from here, we are looking for the variance, right? We end with the variance. So let's do it really quick. Variance of Vx so Vx is E of x squared minus mu squared, right? First thing we need to find is E of x squared. So which is gonna be sum of x squared, P of x equals to little x. So you do 100 squared times the probability is 0.05 plus 0 squared times 0.5 plus, what is it, minus 20 squared times 0.45. So 100 squared times 0.05, you get 500 and plus 0. 20 squared is 400 times 0.45, you get 180, which is 680. So the variance is going to be E of x, big X squared minus mu squared, which is expectation. So 680 minus mu is minus 4 squared. Be careful with the sign here. We have negative sign. So 680 minus 4 squared is going to be 16 with a positive sign. So 680 minus 16 is 664, like that. Okay. Here mu is EX, right? We calculated this before. And if you're looking for the standard deviation, it's gonna be, so this is sigma square, which is the variance. Standard deviation is gonna be square root of 664, 25.77. That's it. All right, I would stop here because it's 1 minute over. Thank you for your time, and we will continue next week with one more example here, and then move on to binomial and normal distribution next class. All right, and I will see you on this Friday in class. We have lab, okay, about the variance in chapter 2. Okay. All right, I will put the notes here in case I think it's quite fast. I will put the notes in Mango. All right, if you have any question, see you. Thank you for the notes. Thank you for the notes in chat box. Bye bye everyone. See you on Friday. Make sure to come to the lab because we have, don't forget, we have 30% for the lab. And for those who don't show up in the lab, will get 0 on the worksheet. Even you turn in, I will give you 0 if you don't show up in the lab. Okay? All right, see you. Bye-bye. Yeah.